Hi everyone, let's try to do a textbook problem for Unit 8. Just remember that in previous videos we had discussed pH and the acidity constant, but we had not discussed yet percent ionization. And I have two problems set up where we have to calculate pH and percent ionization. Let's read the first problem. Calculate the pH and percent ionization in a 0.25 molar solution of hydrocyanic acid, and they gave us the Ka. Just jumping ahead, problem 2 is the same question except they changed the concentration. It was diluted. But let's tackle problem 1 first. When in doubt, I think we're a little more comfortable if we see a chemical reaction, if a chemical reaction is happening. We have HCN, which is a weak acid. I only know it's weak relative to the 7 strong acids that we need to memorize in a previous video. And why don't we just go ahead and put the states, aqueous, plus water, liquid, goes to, in equilibrium, hydronium, aqueous, plus the conjugate base, nitrile anion. Okay. Is there anything I want to say? Oh, we have to find pH. Okay, and we know that pH is the negative log of hydronium at equilibrium. So if we can get this number, we get the pH, and I can show you how to do the percent ionization as well. We're doing an ice table because we are given initial concentrations, but we don't know how much product we get based on the Ka given. HCN starts out at 0.25 molar. Okay, and I like to remind myself that we are using molarity for this ice table. Water is a liquid, so that is not considered in the equilibrium expression. And we start out with 0 products. Minus X, and then for every molecule of HCN we break up, we get 1 molecule of H3O plus and 1 molecule of cyanide anion. Complete your ice table. Okay. The next step, if you recall, is to write the expression. We're not using Kc. Kc, the equilibrium constant for an acid-base reaction, has a special name Ka. But it's still the same thing as before, products over reactants. Double check yourself, make sure that your notes match mine. And we are given a Ka. And yes, just like for equilibrium ice tables, we can use the x to small approximation. We're going to guess it's valid, and then we'll verify it later, but we're guessing it's valid because it's such a low Ka, 10 to the minus 10. But let me show you the setup first. So products, right? Those two multiplied as x times x, and we have 0.25 minus x. If I use the x to small approximation, I want to make sure my graders know that that's what I'm using, and I cross it out. Okay. I typically rewrite it. Where should I rewrite it? I'll read it way to the left. 4.9 times 10 to the minus 10 equals x squared. Now it's over 0.25. If I had not done that and I had cross-multiplied and expanded the terms, we would have had to use the quadratic formula to solve for x. But this is an shortcut if x is sufficiently small, and we're going to double check that in just a bit. First we have to solve for x. .25 times 4.9. Let me just make sure this is going to work. Let me do 4.9 first. 4.9 times 10 to the minus 10 equals times 0.25 equals. That equals x squared, so I take the square root of both sides. Equals. Let me get into scientific notation. 1.107. Yes, times 10 to the minus 5. That's a molarity, and it represents the molarity of hydronium and Cn-. But we want to verify that x is small compared to the initial amount of HCN. So this is your check. And the check is that x has to be 5% or less of the initial amount. 1.107 times 10 to the minus 5 divided by 0.25. Don't forget it's a percent, so it's called the 5% rule. So multiply by 100%. I have the number saved. Divided by 0.25 times 100. Let me get out of scientific notation. So that is a percent already because I multiplied by 100. That's 0.0044%. Definitely less than 5%. And let's tell the grader that we know that this is valid. Then we could just plug in. Actually, for your equilibrium problems, they typically ask what are the equilibrium concentrations of each component. But in this acid-base unit, we're looking for pH. There is a hydronium concentration. We know that pH equals negative log of the concentration of the H3O+. That is, for us, 1.107 times 10 to the minus 5. And then that pH equals, let's see, so I don't have that number saved anymore, 1.107 times 10 to the negative 5, and to the log of that, and then it's a negative, so times negative 1, 4.96 is the pH of a solution of hydrocyanic acid where it was made up to be 0.25 molar. Now, what about this percent ionization? That literally is what percent of this molecule broke up into its ions. And so we do have the number of ions, the molarity of ions, and we do have the initial amount. So this percent is, remember, it's part divided by whole. So whenever you have a percent, you think of it as part divided by whole times 100%. And the part now is how many hydronium ions. Because if we have one hydronium ion, that means one of this molecule broke up. So the part, we are using that molarity, 1.107 times 10 to the minus 5, and the whole is what it started out as, 0.25 molar times 100%. So I think some of you are realizing, well, isn't that the same as the check? Actually it is. We were doing this calculation to check that the excess mol is valid. We're doing this calculation because that is the percent ionized. What percent of this 0.25 became H3O plus and Cn minus? So we do have the answer already, and that is literally the percent ionized. So why don't we just put that there, ionized, circle, And those are your two answers. What you notice is that, this pH is below 7, so it is acidic. The solution is acidic, and you don't need much. You don't need much of the acid to ionize for the pH to register around 5. Okay. Well, the second problem I think is interesting because we could figure out trends. What happens if you dilute a weak acid solution? Will the pH go up or down? If it goes up, it got more basic. If it goes down, it got more acidic, and we're diluting the acid. But we could also figure out what trend occurs when it's diluted, and how does ionization change? Does it get more likely to ionize, or does it become less likely to ionize when you dilute a solution? Should we do this problem? Yeah, let's do this problem as well, real quickly. Before I do it, why don't you pause the video and try it yourself, because I'm going to work through this pretty fast, because it's essentially the same thing. The only thing that I would worry about is extra small valid, but because we start with a lower concentration. Go ahead and pause the video and do your work. Okay, so like I said, I'm going to do this fairly fast, but let me at least get my chemical equation again. I'm going to leave out the phases. If something is different between yours and mine, go ahead and put a mark, we'll just mark it. Actually, I don't know if I'm right. This is the first time I'm doing this problem. I see. I normally wouldn't take all these shortcuts, but it's the same acid, it's the same Ka, and it's the same setup, except now we're going to change the initial amount. I'll even skip all the way down and figure out x and not rewrite the new equation. Okay, so x is definitely smaller than original. But also our initial amount. So let me do the check. Make sure it's less than 5%. The percentage is bigger, but it's still well below 5%. Hence, do you see that? This is valid. Okay, pH. The pH got larger 5.71. With a more concentrated solution, oh, that makes sense. With a more concentrated solution of acid, the pH is lower, more acidic than after dilution. So yes, the pH got more basic. It got bigger. It's less acidic. We diluted it. But what about the percent ionization? Percent ionization, or percent ionized? Well, that's this number. It's the same idea that we saw before. So 0.026% is the percent ionization or percent ionized. What happened? With dilution, the solution, first of all, it became more basic, or we could say less acidic. How about that? Got less acidic, even though what happened? A greater percent of it became ionized, even though a greater percent of HCN was ionized. So not a greater amount of HCN was ionized, a greater percent of the original amount was ionized. Okay. Let me double check if that's all I want to say. That's all I want to say. Okay. Those are your trends when you dilute an acidic solution. Obviously, the pH goes up because it gets less acidic. But again, more water, more volume by which the acid can ionize, less likely that those ions are going to be crowded and the Cn- is going to pick up the proton to go back to the neutral acid, or go back to the acid. Okay, so you can think of this several different ways when you dilute a solution. What's happening at the molecular level.